The modern world has given you a set of templates. Predators look like lions or sharks, built for killing in ways you can read instantly. Herbivores look like elephants or hippos. Massive, but familiar. Everything fits into categories your brain understands. The prehistoric world wasn't running the same process at the same stage. What it produced, across the Cambrian, the Permian, the Cretaceous, the Pliocene, were solutions to biological problems that the modern template doesn't prepare you to recognize as solutions. Animals assembled from what look like mismatched components, body plans that researchers misidentified for decades, because nothing in the modern reference set provided a framework for correctly interpreting them. These animals are not the largest, the fastest, or the most dangerous creatures in the prehistoric record. They are something more specifically unsettling than that. They are the ones that make the design space itself feel wrong. The saber teeth are where the wrongness starts. Not because they're unfamiliar, but because they're almost familiar, and almost is worse than completely foreign. Thylacosmilus, atrox, operating across Pliocene South America, roughly 9 to 1 million years ago, carried canines extending well below the jawline, a feature immediately recognizable as the saber-tooth morphology associated with Smilodon and the Nigersaurus cats. The association your brain makes automatically is the problem. Because Thylacosmilus was not a cat. It wasn't related to cats. It was a sparassodont, a metatherian, more closely related to modern marsupials than to any felid, that occupied the saber-tooth configuration through a completely independent biological history, across a continent that had been geographically isolated from the placental carnivore lineage for tens of millions of years. Biological design produced the same answer twice. From completely different starting materials, across completely separate lineages, the same morphological solution to the same ecological problem emerged independently on the same planet. That's the specific strangeness Thylacosmilus represents. Not the animal itself, but what its existence implies about the biological design space. The saber-tooth configuration isn't a cat invention. It's a solution the design space contains, discoverable from multiple starting points, reproducible across lineages that share no recent common ancestor. How many other solutions does that space contain that the modern world shows only one version of, or none at all? The differences between Thylacosmilus and Smilodon are where the wrongness deepens. The skull structure doesn't match felid proportions despite producing similar canine morphology. Bony flanges on the lower jaw protected the canines when the mouth was closed, a structural feature Smilodon didn't require in the same form. The canine roots extended up into the skull above the eye sockets, meaning the teeth were anchored in the cranium in a configuration no modern predator carries. The brain cavity was proportionally smaller than the Nigersaurus cats. Same answer, different architecture underneath. The woolly mammoth is the prehistoric animal most people think they understand, which is precisely why the actual biology is worth examining carefully. Mammothus primigenius, operating across the Pleistocene mammoth steppe from roughly 400,000 to 4,000 years ago, has been preserved well enough in permafrost. Intact specimens, stomach contents, skin, and hair samples, that the physiological detail available exceeds almost any other extinct species. That detail produces an animal considerably more complex than the familiar icon suggests. The fur wasn't simply thick, it was a layered system. Long outer guard hairs, reaching 90 centimeters providing weather barrier, a dense undercoat of fine wool providing insulation, and sebaceous glands producing oils that prevented the coat from becoming saturated in wet snow conditions. The ears were reduced to roughly 1/3 the size of modern African elephant ears, minimizing surface area for heat loss. The hemoglobin in mammoth blood, recovered from preserved specimens and analyzed genetically, had specific mutations allowing oxygen release at low temperatures that modern elephant hemoglobin doesn't carry. The cold adaptation wasn't cosmetic. It ran through the biochemistry. The social complexity inferred from behavioral analogy with modern elephants and supported by fossil site distributions describes herds with matriarchal structure, long-term memory of migration routes across the steppe, and calf-rearing behavior requiring extended investment from multiple herd members. These weren't megafauna lumbering passively through a frozen landscape. They were cognitively sophisticated, socially organized, physiologically specialized organisms that had been optimizing for the mammoth steppe environment for hundreds of thousands of years. The extinction arrived in a geological instant, a combination of climate shift compressing the steppe habitat and hunting pressure from anatomically modern humans, and removed them from ecosystems they had dominated across timescales that dwarf the entirety of recorded human history. The familiar icon is a simplification. The actual animal was considerably more. Scale is usually a relative concept. Anomalocaris made it absolute. Operating in the Cambrian seas roughly 500 million years ago, Anomalocaris canadensis reached 1 meter in length in an ocean where complex animal life was still assembling its first body plans, and the vast majority of organisms were measured in centimeters. The ecological relationship between Anomalocaris and its prey had no modern parallel, not because the modern world lacks apex predators, but because no modern apex predator exists at a size ratio that disproportionate relative to everything sharing its ecosystem. Nothing alive today is the equivalent of 1 meter long in a world of centimeter organisms. The compound eyes carried visual acuity estimated comparable to modern dragonflies, in a Cambrian ocean where most prey organisms hadn't yet acquired sophisticated visual threat detection systems. 2 grasping frontal appendages handled prey capture. The circular jaw structure collapsed inward during feeding, processing prey through a radial compression mechanism that has no direct modern equivalent. In the Cambrian context, Anomalocaris wasn't hunting in an ecosystem running an established predator-prey arms race. It was hunting in an ocean where the prey side of that arms race was still in its opening moves, where the shells, the escape speeds, the sensory detection systems that eventually made complex marine prey difficult to catch were still primitive or absent entirely. Anomalocaris wasn't a highly refined predator competing against highly refined prey. It was an early solution to predation operating against prey that hadn't yet developed a meaningful response. The strangeness isn't the body plan, though the body plan is genuinely strange. It's the temporal position. Apex predator at the dawn of complex animal life, hunting in an ocean that was still figuring out what animals were, in a body that researchers spent considerable time misidentifying because the modern reference set contained nothing close enough to anchor the reconstruction. The skull is where Nigersaurus stops making sense by any sauropod standard. Nigersaurus taqueti, a rebecosaurid sauropod from Cretaceous Niger, roughly 115 to 105 million years ago, carried over 500 teeth arranged in a straight battery across the very front of the jaw, not distributed through the mouth in the way most dinosaur dentition was arranged, but lined up in a row across the anterior edge, packed so densely that replacement teeth were stacked in columns behind each functional tooth, up to 9 replacement teeth per position. The entire battery replaced itself every 14 days. The jaw was wider than the skull was long, oriented forward and downward in a configuration that functioned as a biological lawn mower. The animal moving its head in sweeping horizontal passes across low vegetation. The dental battery processing material at a rate the rapid replacement schedule was specifically built to sustain. The skull surrounding this dental battery was almost not there. Bone struts thinner than cardboard held together a structure that was mostly air, fenestrae, the large openings that reduce skull weight in dinosaurs, occupying so much of the cranial volume that the structural material was reduced to the minimum geometry capable of holding the teeth in functional position. The nostrils were positioned so far back on the skull that the face was essentially jaw with nostrils attached as an afterthought. The head was held parallel to the ground rather than elevated. Unlike most sauropods, whose long necks implied vertical browsing, Nigersaurus's neck was optimized for horizontal reach across low ground cover. The result was an animal that solved the large herbivore problem by becoming a processing machine, sacrificing the visual impact of the sauropod body plan for a feeding efficiency so specialized that it looks, from the skull forward, like nothing else the dinosaur lineage produced. From the neck back, it was recognizably a sauropod. From the neck forward, it was something the template doesn't account for. For over a century, researchers knew the whirl existed. They couldn't agree on where it went. Helicoprion besonawai, a shark-like eugeniodont operating from the Permian through the early Triassic, roughly 290 to 250 million years ago, is represented in the fossil record primarily by its tooth whorl, a spiral arrangement of teeth in a continuous coil, the oldest and smallest teeth at the center, progressively larger teeth spiraling outward. The structure preserves well. What it attached to does not. Early reconstructions place the whorl on the dorsal fin, on the snout as a rostral weapon, on the lower jaw in various configurations. The correct placement, inside the lower jaw, with the whorl rotating through the bite cycle, wasn't confirmed until biomechanical modeling resolved the mechanics in the early 21st century, more than 100 years after the first specimens were described. The whorl rotated as the jaw closed. Soft prey tissue drawn into the mouth was carried inward and backward along the spiral geometry while being simultaneously cut through. A biological rotating saw processing prey in a single continuous jaw movement requiring no follow-up strike. Contact and completion were one event. The mechanism didn't grip and hold. It processed and finished in the interval of a jaw closing. Helicoprion wasn't a shark. It was a eugeniodont, related to ratfish, positioned in a lineage that has no living representatives with anything resembling the whorl anatomy. The shark silhouette your brain assembles from the description, large, Permian, marine, predatory, is a misidentification your nervous system produces automatically, reaching for the closest modern template, finding a template that doesn't fit. The century of physical misidentification by professional researchers was the formal version of the same process. Nothing in the reference set was close enough to anchor the reconstruction correctly. The animal was strange enough that knowing what it was didn't help place it. For 49 years, the arms were all there was. Discovered in the Nemegt Formation of Mongolia in 1965, Deinocheirus mirificus was known for nearly 5 decades from 2 forelimbs, 2.4 meters each, clawed, heavily muscled, attached to a shoulder girdle suggesting a body of considerable scale. The name translates as terrible hand. The arms implied something catastrophic, a predator architecture at a size that placed it in the upper range of Cretaceous theropod threat levels. The claws suggesting prey capture capability commensurate with the limb dimensions. Researchers speculated. The speculation ran towards something large, dangerous, built around those arms in the way a predator is built around its primary weapons. The complete skeleton, recovered in 2014, disclosed an animal that violated every expectation the arms had generated. The body was massive, 11 meters, 6 tons, but the head was small and duck-billed. A hadrosaur-like skull on a theropod body. A prominent neural spine hump ran along the back, reaching heights suggesting a bison-like dorsal profile. The stomach contents included fish remains and gastroliths for plant material processing simultaneously. an omnivore, consuming from multiple trophic levels. The enormous arms functioning not as predatory weapons, but as foraging tools for sweeping vegetation and accessing aquatic food sources. The claws that implied prey capture were raking implements. The arms that implied a predator were a herbivore's reach extension. The gap between what 49 years of arm-only evidence implied and what the complete animal actually was is the cleanest illustration the prehistoric record provides of how thoroughly the modern template fails as a predictive tool for prehistoric biology. The design space at work produced an 11-meter, humpbacked, duck-billed, fish-eating, plant-processing theropod with 2.5-meter arms. It was assembled by 165 million years of theropod history, working in a design space that the modern world has closed most of the doors to. The arms were terrible. The animal behind them was something no one predicted. That's the point.